Hi, this is an example problem from chapter 14, and this is just some additional practice when you're dealing with changes in the state variables for the ideal gas. When you have ratios of changes, how do you calculate these? So let's practice a couple of these. In the first case, we have a gas that's going to be heated at a constant volume until the pressure quadruples. By what factor does the temperature change? So we're trying to figure out in this case, let's call the initial state 1 and 2. So, in state 1 and in state 2 over here, we're going to have our variables for the ideal gas law. P1, V1, T1, and I'm going to use little n1 here. For the other one, P2, V2, T2, N2. The ones and the twos just correspond to different states of the gas. Something's changed, so the variables have changed. But they're still related with the ideal gas law. So we want to basically go through each of these and see which of these things have changed by how much and which are the same. So for part A, it's heated at a constant volume until the pressure quadruples. So V2 is equal to 1 because the volume is constant. It hasn't changed. Now the container is sealed, so the number of moles hasn't changed. And so we've got these guys being the same. Now the pressure is quadrupled, right? So P2 is equal to 4 times P1, and we're asked to figure out by what factor does the temperature change. Okay, so we're going to try to figure out in part A, what is T2 over T1? That's the factor by which the temperature changes. I'm going to do this just like I've done this before. PV equals nRT, right? Well, I'm going to write nRT equals PV. And I'm going to put the 2's here because I want the T2 to be on the top there. And now I'm going to divide both sides by the same ideal gas law equation. Since it's equal, I can divide this side by N1, RT1, as long as I divide the other side by P1, V1, because it's equal to N1, R1, T1. Now what we're going to do is look at the ones that are the same. And we're going to just cancel them out because they divide out. So N1 and N2, R didn't need a 2. And what else is the same here? The volume is the same. So we quickly get a relationship that relates the temperature to the pressure change, right? So just to see this more clearly, the ratio T2 to T1 is equal to P2 over P1, and we know what P2 is. It's 4 times P1, and so we end up with a ratio of 4. So just like the pressure quadrupled, in this case, the temperature also quadrupled. Let's look at another one real quick. So for part B, let's go ahead and see what this one says. The gas is rapidly compressed to 1/20th its initial volume. So let's go and say that the volume here is going to change, right? So these aren't the same anymore. V2 is equal to V1 divided by 20. It's been compressed, causing the pressure to increase by a factor of 60. So P2 is now equal to 60 times P1. By what factor does the temperature change? Again, we're looking for a temperature change ratio, T2 divided by T1. And we also do, again, have a closed container, so it's still the same for the number of moles. All right, let's go ahead and set this up again. So I'm going to go ahead and what I want to do here, let's get rid of this for a second. I want to get T2 over T1, so I'm going to do the same thing I did before, N2, R, T2 equals P2, V2. Divide both sides by the initial condition. Then we're setting up the ratio already that we want, T2 over T1. And then we've got P1 over V1. All right, let's cancel the things out that are the same. So this is gone. Those are gone. And let's go ahead and write that T2 over T1 is equal to, now, P2 V2, right? But I can plug in for P1. Actually, no, I did that wrong. The ones that we know here, P2, I can plug that in. 60 times P1, that's P2, and V2 is equal to V1 divided by 20. And then we've got P1, V1 in the bottom. And we can go ahead and cancel directly the P1s and the V1s, which will leaves us with a 60 divided by a 20, which tells us that the ratio of temperatures, it has increased by a factor of 3.